Welcome to my video lecture on electric circuit theory. Paper code PCE 301. This syllabus is included in the markout curriculum, and the topic I am highlighting here that is based on graph theory. Topic here is tie-set matrix and part-set matrix. Myself, Guru Banerjee, Assistant Professor of Electrical Engineering Department, Dr. Sudhir Chandrasu Institute of Technology and Sports Complex. Previously, it was known as Dr. Sudhir Chandrasu Degree Engineering College under GIS Group. In my previous lecture, I have highlighted about the topics of graph theory, and there I have discussed what is graph, what is node, branches, part-set matrix, tie-set matrix, and how by using tie-set matrix we can form the KCL equations, and how the graphs can be formed, how tree, co-tree can be drawn, what is linked. Those things we have highlighted in my previous lecture. In this lecture, we will talk about tie-set matrix and its KCL and KVL relations, and also the cut-set matrix and its properties, and how the cut-set matrix will be developed in case of graph theory that has been shown in this lecture. So, let us start with tie-set matrix and KVL. For example, we have taken a graph which is shown in the figure, and from the graph we know that we will omit those branches which will form the loops of the graph, and the remaining part will be the tree. So here 4.7b is the tree, and each and every loop we have separately taken. So from the graph shown in the figure and the three loops shown in the figure C, D and E, the three fundamental mesh KVL equations can be written as follows. For fundamental loop 1, here VB1 is the branch voltage or branch 1. VB3 is the branch voltage at branch 3 and VB2 is the branch voltage at branch 2. So in the loop we have seen that the loop is formed in between 1, 2 and 3, and the direction of the loop is 2 and 1 in the same direction and 3 in the opposite direction. So the sign of 2 voltage between the 1 and 2 will be positive and 3 will be negative. So in that way we have formed the equations of loop 1, that is VB1 minus VB3 plus VB2 equals to 0. And similar way we have formed the equation of loop 2, that is VB2 plus VB4 plus VB5, that is equals to 0. And also the fundamental loop which is formed by this third loop and which is combination between 3, 4 and 6. 3, 4 and 6. So definitely the KVL equation for this loop will be combination of VB3, VB6 and VB4, and all the directions are same, so the signs will be positive. So it will be VB3 plus VB6 plus VB4 equals to 0. So from these equations we can form the incidence matrix which will be combination of 1 and 0. So for the first equation, it is at branch 1, 3 and 2. 1, 3 and 2. So it will be in position of 1, it will be plus 1, in position of 3 it will be minus 1, and in position of 2 it will be plus 1. So in that similar way 1, 1, minus 1, and remaining all the 3's and 4, 5, 6 are not connected, so it will be 0. Similar way, in position for equation 2, in position 2 it will be 1, in position 4 it will be plus 1, and in position 5 it will be again plus 1. That means 2, 4 and 5, in these three positions there will be 1. like this. Okay. So in that way we have formed the incidence matrix, and here we have put the all branch voltages, and this will be equals to 0. That means VA into VB equals to 0, and that is the tie-set matrix and KVL relation, the relationship between Kirchhoff's voltage law and the tie-set matrix. In that way, we can write down the KVL equations and form the tie-set matrix and its corresponding tie-set matrix we can form. Similar way, for tie-set matrix and KCL equations, we can also do the same way for that same graph, which is 4.78, and using the tree and all the nodes, we will calculate the branch currents IB1, IB2 and IB6, which has been represented as loop currents in case of IL1, IL2 and IL3. That means the currents here IL1, this will be IL2, and this current will be IL3. Okay. So in that way we can form the loop currents also. So here IB1 minus IL1, IB2 minus IL1 plus IL2, IB3 minus IL1 plus IL3. In that way we can write the loop currents also, and from there we can form this matrix of each branch current. That is IB1, IB2, IB3, IB4, IB5, IB6 equals to incidence matrix transpose into IL1, IL2 and IL3. That means branch current IB equals to BA transpose IL. So in that way we can form the tie-set matrix and Kirchhoff's current law equations. So now we will come to the point of cut-set matrix and node pair potential. So first of all, we have to know that what is cut-set matrix. A cut-set is a minimum set of elements that, when cut or removed, separates the graph into two groups of nodes. A cut-set is a minimum set of branches of connected graph such that the removal of these branches from the graph reduces the rank of the graph by 1. That will form the cut-set. Okay. So it is basically a minimum set of elements when cut, removed or separate from the graph into two group of nodes. Then it is called cut-set. Okay. That means we will remove particular branches from two separate nodes, and which will ultimately reduce the rank of the graph by 1. In other words, we can write that a set of branch C is defined as a cut set if and only if the removal of all branches of C result in an uncounted graph, or the removal of all but one of the branches of C leaves the graph will be still connected. So, first of all, we know what is fundamental cut set. A fundamental cut set is a cut set that cuts or contains one and only one tree branch. Therefore, for a given tree, the number of fundamental cut sets will be equal to the number of twigs. Okay. So, first we have to know that how we can do the fundamental cut set. So, for this process, we have first one, select the tree of the graph. First, we have to choose the tree of the graph. Second, focus on the tree branch. Third, check whether removing these tree branches from the tree disconnect the tree into two separate parts. Okay. Fourthly, all the links which go from one part of this disconnected tree to another together with the tree branch form a fundamental cut set. So from this following process, we are getting 3 number of cut sets, and and it will be combination of 1 to 6 for the first cut set as per the given graph. This one. First cut set is 1 to 6, second cut set is 2, 3, 5, 6 and third one is 4, 5, 6. So here we have taken the cut set from this node 1 side, or we have taken the cut set from node 4. And in that way we have started the portions and we will see that it has been separated or not. And the cut set must maintain some properties. First one, a cut set divides the set of nodes into two subsets. Secondly, each fundamental cut set contains one tree and the remaining branches are being links. And in the per tree, each branch of the cut set has one of its terminal incident at a node A in one subset and gives the other terminal at node in the other subset. So in that way we can form the cut set matrix, and we have to maintain all these properties of the cut set matrix, and we have to verify that whether we have formed the cut set that is actually a cut set or not by verifying the tree and the cutted link. So from there we can verify the cut set is actually formed or not. Now cut set matrix formation. So for a given graph, a cut set matrix QC is defined as a rectangular matrix whose rows correspond to the cut set and columns correspond to the branches of the graph, and its elements have the following values. So what will be the values? That will be, if the cut set matrix is Qij, that is this one, Qij equals to 1 if the j is the cut set of I and orientation coincide. Again, Oij equals to -1 if branch j is in the cut set I and the orientation do not coincide. Next, Oij equals to 0 if the branch is not in the cut set of I. So in that way we can form the cut set matrix. Okay. So now we will see the cut set matrix and KVL relation. By cut set schedule, the branch voltages can be expressed in terms of 3 branch voltages. A cut set coincides of one and only one branch of the tree together with any links which must be cut to divide the network into two parts. A set of fundamental cut sets include those cut sets which are obtained by applying cut sets division for each of the branch of the network tree. So let us, this is a graph which is shown here, this one, and we have figured out the tree of this graph, this one. Now applying cut set at node A, B, C and D as per the figure, we can write the cut set schedule as follows. So applying cut set in 1, we will get the relationship between 1, 4, 5. In the first cut set, this one, we have seen that this cut set is related with 3 branches, 1, 5 and 4. And 1 and 4 and 5, see the directions. 5 and 4 in the same direction, 1 in opposite direction. So 1 is in minus and 4 and 5, that will be plus. Similar way, if we see the cut set at point B, this one, it is connected with 1, 6 and 2. Here the direction of 2 is entering and direction of 1 and 6 are leaving. So 1 and 6 will be positive and 2 will be negative. In that way, we will form this cut set matrix like this one. Now, the three branches voltages are VT3, VT6, VT7, VT8, and the branch voltages are VV1, VV2, VV3, VV4, VV5, VV6, VV7, and VV8. And the relationship between these three branches and voltages are like this. That is, VV1 is minus VT5 plus VT6. How? See this one? VV1 is combination of VT5 and VT6. Okay. VV1 is combination of VT5 and VT6. VV2 is combination of VT6 and VT7. See, VV2 is combination of VT6 and VT7. Okay, that is also right. Next, VV3. It is combination of VT7 and VT8. Next, VV3. This one, 3. It is combination of 8 and 4. Yes, it is combination of 8 and 4. And VV4 is VT5 and VT8. See, VV4. This one. VV4. It is combination of 8 and 5. Okay. So, all these things have been formed. So, putting those things, we can form the cut set and KVL matrix like this way, where VB equals to QCT transpose into P. So, that is the relationship between the Kirchhoff's voltage law and cut set matrix. Now, we will do the cut set matrix and KCL in a similar way. Here, in place of voltages, we will put the currents and we will form the KCL equations at node A, KCL equation at node B, KCL equation at node C, KCL equation at node D. And from these equations, we will form this cut set matrix and the combination of QC into IB, that will be equals to 0, and that is the cut set matrix and KCL relation. Now we will see an example of graph theory. So let us consider this is a circuit given. From this figure, we have to form the graph first, then find one tree, and then find how much mesh currents are required for solving the network and the number of possible trees. These things we have to find. So first we have to draw the graph. So for doing the graph, for this loop, this is this loop. Next, this part is this one. Next, this is the capacitor part. This one. Next, this is the resistance part. This one, resistance part. Then this is inductor and resistance. This one, inductor and resistance. And this is the voltage and capacity. This is the voltage and capacity. So in that way, we can draw the graph. Okay. So now from the graph, we will remove all the branches which will make a loop. So after removing this, we can find the tree. So here we have removed this one, remove this one, remove this one, remove this one. Okay. Then we can get the tree. Now from the graph, we will form the incidence matrix, and from the incidence matrix, we will form again the reduced incidence matrix by removing one row. Now after Making a reduced incidence matrix, we will do the determinant of reduced incidence matrix into transpose of reduced incidence matrix, and its determinant will give us the number of possible trees. And we have got here that the number of possible trees is 12. So in that way, we can solve the problem. Okay. So up to this much for today's lecture. And in this lecture, we have mainly discussed about Cartesian matrix, Dirichlet matrix, and KCL-KVL relations, and we have solved a numerical problem related to this. And in this topic, we will cover some problems related to graph theory for easier understanding. Graph theory is very important topic for all of us, and it is very important topic also for semester examination. It is very easy to solve, and it is also very important for getting good marks. It is very scoring part of circuit theory. So I will prefer that you can go through the books of O.V.G. Chakraborty, or you can go through the book of Subhadeep Bagchi of circuit theory in this regard. And for this purpose, I will tell you, in circuit theory, all of you must practice the problem related to graph theory also. So it will be very easy for you to answer the questions, and also helpful for you to secure a good marks in circuit theory exam. So what more today? Thank you all for listening my lecture. In my next lecture, I will discuss some problems related to graph theory, and that will be the last lecture of graph theory related to circuit theory, PCB 401 select. So thank you all.